Another couple of examples dealing with angles are linear and angular speeds. So when we think about linear and angular speeds, let's talk about, we know that velocity is given to be some sort of change with respect to time. And that's really what we're dealing with here. We're dealing with some sort of linear velocity as well as an angular velocity. So for our linear velocity or linear speed, we have the arc length, which is changing with respect to time. And for angular speed, down here, we have the angle, which is changing with respect to time. So what does that look like? Let's go back to our circle here. If I have a circle which has some radius r, and I'm going to have a point that's going to travel around the circle, and let's say the point stops here, or let's make it go here. So my point stops here. The distance that this point has traveled would be considered the arc length. What we want to know is what is the velocity with which this point is traveling around the circle with respect to time. And that has to do with the arc length with respect to time, or s over t. Now, angular speed, we know that this point, as it's traveling around the circle, is going to have rotated some value of theta. So angular speed has to do with the change in theta with respect to time. So the angular change, or that change in theta with respect to time of this point that's moving around the circle. So these are the two formulas that we're using. We have linear speed, which is defined by v, that's equal to arc length over time. And we have angular speed, which is given by omega, it looks like a cursive W, and that's given by theta over time. We have a couple of different variations of these formulas that we can look at since we already know how arc length is defined, and they can be kind of helpful to us. So this is what's being defined over here. Coming back to our formula here, we defined earlier that arc length was equal to r theta over time. But now we're introducing the fact that theta over time is equal to omega. So I could rewrite linear speed as velocity is equal to r omega. So what you're seeing here is three different variations of the same linear speed formula. It just depends on what you have and how you want to use it. One other note to keep in mind here, we know that when we're using these applications for arc length and linear and angular speeds, we're making applications for radians, and therefore, or angles I should say, and therefore theta must always be in radians. We can use the idea that one revolution around the circle is equal to 2 pi radians, and this is going to be a conversion that we're going to be finding useful for us whenever we are dealing particularly with angular speed. We'll see it come up again in just a moment. So this example that we're going to look at says that we have a 7¼ inch circular power saw blade that rotates at 5,200 revolutions per minute. We want to first find the angular speed of the blade in radians per minute, and then we want to find the linear speed in feet per minute. So we're going to tackle first our angular speed. Remember, we defined angular speed as theta over time, whereas we had some sort of angle change with respect to time. Now, the only angle change that we have going on is in reference to theta, has to do with this 5,200 revolutions per minute. So what am I going to do with that? Well, let's start by converting our revolutions into radians. So when I do that, if I have 5,200 revolutions, and in fact, I'm going to write this for us a little bit differently. We're told already that we have 5,200 let me put it to you this way. We have 5,200 revolutions per 1 minute. So automatically I have kind of my angular speed set up, but I don't have it in the right unit. So I have revolutions per minute and I need it to be in radians per minute. So we're going to use this conversion factor here, which says that 1 revolution is the same as going around the circle 1 time would be the same as 2 pi. So when I now look at this, you'll notice that my revolutions canceled and it's leaving me in radians, which is pi, over minutes. So I now have my angle with respect to time taken care of, and now it's just a matter of multiplying. So if I multiply straight across, I'm going to end up with 5,200 times 2 pi. If I wanted to find the approximate value or the decimal value, that would end up being 32,672.6 radians per minute, which is what we were asked to find this in. The second part of this question asks me to find the linear speed. So linear speed is going to be, remember our linear speed v was defined in 3 ways above. We can define it in terms of arc length over time, the radius times theta over time, or the radius times omega. A lot of times, if we already know what omega is, we can just use the shorter version of that formula, r omega, to be able to solve our problem. Don't forget, however, we are being asked to solve this in feet per minute. So we're going to end up doing a little bit of changing here, feet per minute as well. So our saw blade is defined for us up here as a 7 1/4 inch saw blade. That's actually the diameter of the blade. So the diameter is 7 1/4. That would give us a radius. If I divided 7 1/4 by 2, that would give me a radius of this blade at 3.625 inches. So it's that the radius is equal to, actually that's the diameter, I guess that's what I want to say. That's the diameter of our saw blade. Now, if I know what the radius is in inches, and I also know what omega is from part A above, then I'm just going to multiply r times omega to get the velocity, the linear speed. So the linear speed is going to be equal to 3.625 inches times, now I'm not going to use the approximate value from up here. I'm going to go back to the 5,200 times 2 pi, which ends up being 10,400 pi over 1 minute. And again, this comes from this part up here. So 2 times 5,200 times pi, the exact value would be here. And I'm doing that so I don't end up with any rounding errors right off the bat. I want this to end in feet per minute. I'm currently in inches per minute, and so I would need to now multiply by the conversion factor 1 foot over 12 inches. So this would be over 1 if I set up my unit conversions like this. I have inches, which are going to cancel. This is leaving me in feet per minute, and now I'm just going to multiply everything straight across, and I end up with a approximate value, once I use pi, an approximate value of 9,869.8 feet per minute. That's the linear speed of this saw blade. So with this type of problem, there's some conversions that usually have to happen. I noted at the angular speed point that this was radians per minute, and you'll notice that I dropped it from that portion down here because technically radians don't have any unit. A radian is unitless, but it's easier for us to at least note the fact that we are in radians here per minute, and then I don't really need that information when I came down here because I've got inches, they cancel, leaving me in feet per minute.